Okay, in this example, we're going to actually calculate the EMF. So we're going to draw a picture. We have a loop of wire, and we know that the diameter is, so let's see our givens. Our diameter is equal to 12 centimeters or 0.12 meters. And that means that our radius is equal to 0.06 meters. We know that our B field is equal to 1.5 Tesla. We know that our delta T, our changing time, is equal to 0.2 seconds. And so what's happening, right? So we can do a before and after. So before, it says that our loop of wire is oriented perpendicular to the magnetic field. So I'm going to say, like, the magnetic field doesn't tell us, but I'm just going to assume it's into the page. Or yeah, it's into the page. And I'm just going to draw a magnetic field, and I know that my loop is in that field. Great. And then after, I know, so I'm going to draw that magnetic field again. Right, and now my loop, it's rotated. So at first it's perpendicular, and now it's parallel. So that means it's going to look like I'm just looking at it from the side, right? So so the magnetic field now isn't going through the loop, the whole, the loop of wire. It's since the loop is turned so that none of the flux lines can make it through. So here I'm going to have, like, I'm going to say my B field, or my flux, I guess B here that's going through is 1.5 Tesla. But the B that's going through here is 0 because no flux can make it through because of the way we have this turned. So when I want to use my equation, so my equation is EMF is equal to a negative change in the flux over the change in the time. Okay, so if I want to plug that in, then a negative. And so what's phi? I know phi is equal to B times A. So B, so this is B perpendicular to A, right? And so I'm going to have BA. So my BA is going to be 1.5 Tesla times my area. Let me write this down here just because I need more room. So my EMF is going to equal a negative. Well, I see the formula up there, but it's going to be a negative. And then I'm going to say that this is the final flux minus the initial flux. So the final flux is 0, right? It's 0 because no flux gets through that loop, minus, and now the flux initial. So the flux initial is the B field, which is 1.5 Tesla. And we'll just do this, times the area. And so what's the area? That's going to be pi r squared, right? So my area, let's write that over here. So my area of my loop is going to be pi r squared. So that's what I'm plugging in right here. Pi times r squared is going to be 0.06 squared. And now my time is going to be 0.2 seconds. And if we multiply that out, my EMF is going to be, see, I have a negative here and a negative here. So that means I'm going to have a positive, and I end up with 0.85. And this is going to give me a voltage. right? And then also think about, if you're not sure about the sign or what's going on, if you draw the graph and just make a rough graph, when we say we're going from a lot of flux to none, just think you're starting at some flux value, some non-zero value here. And I don't know the shape, but I know I'm doing something where I'm going down to zero. So it may not be a line, it might be a curve, but it helps to think about this. And it tells me the slope here is negative. And so negative times a negative slope here, right? I get a negative value for this part times a negative gives me a positive. And that's why the flux here is positive.